So let me also put a pointer. So, all right, so today we're gonna go over PCB layout on week 4. We don't have any announcements, and then just as a refresh from last week, you mainly saw about communication systems and also schematic, Ego schematics. PCB layout will build up a lot on like what you have already done on Ego schematics, and thus it will also build up on what you have done on week 2, which was regarding doing the devices, the symbols, and the footprint of everything. So this is how we'll manage our presentation today. Here are some topics we'll cover. And just a quick recap from week 2 and week 3. So on week 2, we created pretty much the devices that we will put in our final board. And each device has a symbol and a footprint. On week 3, you had a solid experience by using the symbols, but you didn't really manage to work so far with the footprint. So the footprint will be used now with the PCB layout, where we actually will be implementing the physical part of the PCB, and thus we're gonna have to have the exact footprint dimensions of each part. So on schematics, we pretty much connected nets between the pins of different symbols. And now with the board layout, we're gonna actually make all of those abstract nets into actual physical traces. So we actually design like the traces of copper that will route the signals around our board. So apart from that, I'll also show you guys later how you can easily change from schematic to board on Ego. And that's something we will mainly address during the lab part of this week. Okay, so a little bit of how's a PCB structure. Also PCB, I think we probably addressed this before sometimes, but PCB stands for printed circuit board. And the way the PCBs are manufactured is they have multiple layers of copper, and they're in the most simple PCBs, they're like top copper and bottom copper. Those are where most of the signals pass through. And then there's also a thin layer called solder mask, which we use for making sure that we are insulating the copper from the outside world, and then we can't like easily short the signals if you like put a finger in your board. And then apart from that, there's also the silk screen, which is pretty much those white names and lines that you see all throughout the board. And as you can figure out, those are in general just more useful for given information for the end user and also for the developer. So in this case, each of the silk screens in the top of this board is like signalizing what each of those pins are for, and silk screen is pretty much there to help the user. And then there's also the element that's inside the board, which pretty much is isolating the copper layers of the board, which is in this case FR4, which is one type of substance, but there's also like other ones available, but you don't need to memorize this. And then apart from that, there's also some spots in the PCB that you see that they don't have solder mask on, because at some parts of this PCB you actually want to have a place in which you can solder stuff at, and you want the copper to be exposed, because if you want, for instance, to solder a resistor, or in this case right here to solder an IC, you can then have those pads available and having their space for putting a component. Okay, so let's go ahead and see a little bit of how that's all represented on Ego. So pretty much on Ego, you have different layers, and all of those layers will have different colors and also have different names. So top and bottom, those are top layer of copper, and then copper bottom layer. In this case, there are also some boards in which there are multiple layers of copper. So for instance, 4-layer boards would have another 2 layers of copper between top and bottom. And then there's also like layers for vias and pads. Pads in Ego are considered the true holes that go from true holes are holes in the board that are copper plated, and we use them for putting components in the board. And similarly, there are also vias. You see that they have like quite similar colors. And vias, we use them for routing signals from one layer to another layer. So pretty much we put a hole through the board, and in certain layer of the board, we connect a signal to the plated copper hole, and then in another layer, we also connect it to the copper to the plated copper hole. And then pretty much now those 2 signals and the same signal, but those 2 traces in different layers, they are now connected between each other. So vias, they help us connect stuff on different layers. And then there's also some important layers that may pass unnoticed, like dimension layer, which pretty much is the outline of the board. So the exact dimensions of the board are defined by the lines in the dimension layer. And then there's also the silk screen that will be on the top and the silk screen that will be in the bottom. So as I told you guys before, silk screen will be used for give the users a little bit of information. So it's gonna you can have it on the top layer and also on the bottom layer. And then for last, there's also T.Q, which is a layer that you will only be able to see on Ego, and it will look like silk screen, so it will look like T-place. However, it won't be actually manufactured into your board. It will be just there so you can see some text in the design itself and like take note of it, but it won't be printed in the board. Most of those you memorize as you use Ego, and you also get used to their colors that normally are kept consistent. So for instance, on Ego, this is the PCB Layout window, which is a bit different from the schematics window that you guys saw previously. And on this window, for changing layers, we're pretty much now talking about layers. So if you want to change layers, there is a place on the top that pretty much says the layer that you can that you're viewing and that you can select with the highest ranking. So you can change layers by going through this menu right here. And then you can also use this tool right here that appears like a bunch of layers. So these bunch of rectangles, one over the other, you can press on there, and then you can set which layers can you view. And then on this board, you see that there are many layers that are being showed at the same time. Okay, so as you transition from your schematic through your board, you want to end up with like something right away like this. Like you actually have to design this. So You will start with a bunch of components out of the board, and they are like all around. So the way that you transition from this empty space for this bunch of components not connected to like the actual board is part of the lab that you will be doing in the end of this presentation. So just going over the steps. So first step, you're gonna have to arrange the components. You get every component and move them around the board. You'll be doing that with the move tool that you have on the left tools of your Ego on the window of the PCB layout. So pretty much you can click on the crosshair of the parts. That's like something that's not so intuitive sometimes, because sometimes you're just gonna try to press anywhere on the port, and sometimes that doesn't work. So go for pressing on the crosshair, drag it, and then if you want to rotate it, you can right click, and with that you can start positioning your components, and also have in mind that you want to minimize the crossings of these guys right here. These are called air wires. Air wires are pretty much showing from which pin to which pin you should be connecting. Air wires by default will try to connect, indicate you. They're not actually connecting anything on the physical board. They're just like indicating from which pin to which pin. So they will indicate from where to where you should connect your signals in the smallest Euclidean path. So like for instance, you have a bunch of grounds in here, and you notice that like this ground will try to create the air wire to the closest ground, and the same in here. But this is just a user-friendly indication tool. It's just like showing you where's the nearest signal that you should be connected, that you should be connecting. So yeah, those are called their air wires. And since you're gonna have to actually make the traces that will like be the wire coppers that connect the pins from the, for instance, from this part to these resistors, you preferably not cross them, because you'll be making the traces right here, and you also don't want the traces in real life to cross. But we'll see later how to go over in situations in which stuff will have to cross. So let's go ahead and let's think about some arrangement considerations. So as I told you guys before, you want to minimize the number of air wires. You also want to know what's the maximum size of your board. For instance, if you're putting your board inside of a robot, you can't make your board very big. And sometimes you just gotta make it smaller and make all your components fit in the space constraints that you have. And then there's also the thing that you must also maintain clearance of your components. We will see later about design rules that they will complain if you don't follow this, which is nice. But then there's also some intuitive like considerations that you should have in mind, and that sometimes are not in the design rules. So for instance, there are some mounting holes in some boards. Mounting holes are the holes that go through the boards, and that you use for like putting a screw through it, and like putting a mounting spacer on your board. So in this case right here on an Arduino, for instance, an Arduino has 1, 2, 3 of the 4 of those mounting holes. So you don't want to put a component too close to it, because you got to remember that you'll be screwing a screw into the hole. So you don't want the screw to go over some component that that exists on your board and like break the component or something. And then there's also some specifics of like where you should put each component. So connectors are normally in the board of in the edge of the board, as it's easier to connect to a connector that's in the edge. And then the coupling capacitors, those are pretty much so we use capacitors very frequently among the whole board in certain places in which we need to smooth the signal that enters some integrated circuits. So those capacitors that we put near those capacitors that we use for smoothing the signal, we call them the coupling capacitors. And they're very commonly put on supply lines for instance, microcontrollers, or pretty much almost every complex integrated circuit. So one consideration that you must have on creating your PCB layout is when you're putting your decoupling capacitors, they need to be near the decoupled pins. So, and the example that I just told you, supply pins for microcontrollers commonly have decoupling capacitors. So in this case, you would put the decoupling capacitor near the supply pin, and you will learn more about this, and you can research more about this on your own. Apart from that, make sure to have components that communicate with each other next to each other for minimizing any loss that you can have while on the communication lines. All right. Also, any questions so far? Okay, then I'll keep going. All right, so continuing on the arranging components, here's an example of a board on the process of just arranging the components. So far we didn't put any wires between anything. We're just like trying to put the components in the best place in our board, minimizing the air wires. So some more considerations you gotta have is like you gotta leave space between the components, because you gotta remember you have to remember that you'll be routing wire traces between them, and sometimes if you don't leave enough space, you wouldn't be able to like make a wire go around and connect two pins. Also, there's another consideration that is sometimes overseen, which is you also gotta have room for soldering. So in the future, when you order your PCB and you have to actually solder it, if the components are all close together, it'll be very difficult to solder everything, because as you solder one component, it will now be like on the way of the soldering iron for you to try to solder another component. So that's especially hard if you want to like solder something or here works something, and here work being this component is wrong, it's broken, and I need to take it off and put it back again. And if it's in a very clustered place with other components, that will be very annoying and hard to do. So apart from that, minimize air wires again. It will make your life a lot easier when you're routing all those traces. Okay, so how will you finally then route those traces? There's a tool on the left bar. Everything pretty much of tools are in the left bar on the PCB layout window, just as you guys had everything of your tools and the schematic on the left bar. So you use the route air wire tool, or you can also write route on the command line. And after that, you can like click on one pin and then click on the other pin, and you will have your wire being connected between two pins. The wire, as you can see here, will follow your cursor. Apart from that, we also have, it's quite common on every circuitry nowadays to have all of the wires connecting pins on pattern of 45 degrees. So in this case, for instance, this is just a line on, but also 45 degrees. And then in here, you see that every curve that we do are 45 degrees. This has been something mostly out of culture from PCB design across years. It was more relevant on past decades with limitations of the fabrication houses that created the PCBs. There's also like some nice online resources talking about why industries actually make everything 45 degrees, and you can look that up more in detail. But also for aesthetics, it's also considered a nice thumb rule of thumb. Okay, so let's keep. And then finally, what you should do when there's literally no way of routing a trace without crossing another trace. So in that moment, you gotta remember that you also have other layers in your board, and you can use those other layers to route your signals. So in this case, let's suppose that the person couldn't like go over here. So like this is all like other traces, and you gotta reach this other pin. So you can start to route, and then you press space, and then Eagle will automatically change the layer with you, and then put a via right there. And then you change the layer after passing through the via, and on the other layer, you will route into the other pin that you want to connect to. Another thing is that instead of pressing space for changing layers, you can also press the middle button of your mouse. All right. Okay, then there's another thing that's quite useful when you're creating a PCB, which are polygons. Polygons are pretty much a region that you select in your board, and everywhere on the region will be copper. So you can choose the different layer that you put that polygon. So for instance, if you want a copper on the top layer or a copper in the bottom layer, you like select the layer that you want to put your polygon, and then you create like those geometric forms that after you run RatsNest, they will properly be created. And then apart from that, polygons also have rankings. So for instance, those two polygons, they had like a common region right here that was like part of both of their regions. So who wins that region? The polygon that has highest rank. And then polygons are very commonly used. Something that you'll notice on the lab and also in any board that you look on RoboJackets is that they all have ground planes. And those ground planes are pretty much planes. Planes you can commonly just change with the word polygon. So they are polygons that stay normally in the bottom layer, but they can also be in other layers. They're commonly in the bottom layer for 2-layer boards, but like you are simply gonna fill out the whole region of your board. You in one layer, you fill it with copper, and then that copper will be connected to your ground. So now you can have any component on your board to simply pull out a trace a little bit to the right, and then you put a via, and and then that's it. The via will be connected to the ground because you previously just put a ground plane on everywhere, and you can easily connect any component to the ground plane. Apart from that, ground plane is very useful for learning the impedance for every component, because you have a very good return path from any component to the ground, and then you can read more about that on the lab. All right. So pretty much you're done with your board, supposing that you know how to position everything, you know how to trace everything, you did a ground plane, you did some other polygons for because you need it, and now you need to actually see if everything is working. So design rules are something that you feed previously to your board, and they will pretty much say if everything is correctly spaced according to like physical constraints. Because, for instance, you can't make two wires too close to each other, or you can't make two wires with different signals touch each other. That wouldn't work in the real world. So you got to make those design rules that will put some constraints and will create warnings and errors that will then alarm you and make you think and make you change your design. Apart from that, those design rules are very important for addressing the limitations of the fabrication houses. So pretty much, if you're gonna send your board to be manufactured by some PCB fabrication house, they have some limitations. So for instance, there's a limitation on how small can your trace be, how small can the minimum hole of your board be. So like the vias, they have like a minimum size, and putting all of those constraints on the design rules of your project on Ego will like help you limitate them by default on your design, and you like will be aware of what you shouldn't be doing. So there's also a very useful tool, which is the DRC, which is the Design Rules Checker. So this tool will basically be used for helping you list all the warnings and errors in your board, and then you can click on every error and warning, and then you'll be automatically redirected to where the problem is happening, and then you can fix it. And then I put a note right here just to remember all of you to like always try loading the design rules as early as possible, because you don't want to make your whole board based on some design rules that actually won't be enough, won't have enough clearances and like spacings. And then in the end, when you put the right design rules, or if you send to the fabrication house, they will complain because what you did is like has too small constraints and doesn't respect what they can actually do, or doesn't respect their capabilities. Okay, any questions so far? If not, there's also another very important tool, which is the manufacturing view. So you have a window on the PCB layout, and on the right there's like this manufacturing button, and as you press it, you will see how your PCB looks like. So it will show all of the pads and the silk screen that you did, and this is very important to like after you finish your board, you take a look at this and see if all of the silk screen looks good, if like no component will be, as you're soldering them, will be like touching each other. So be sure to take a look at this window after you finish your design. And then apart from that, there is also some useful information here that's especially useful when you're like sending your boards to fabrication for manufacturing. which is when you click on boards right here, you will get information about everything of your board. So height, width, area, all of the different layers that you have on your board and their thickness, and also minimum drill size of all of the drills present in your board. Okay. Apart from that, on Eagle, you can use some commands. You can come back into these slides if you don't remember these commands, but like these are quite useful. So first one is rat's nest. We talked a little bit about it on polygons before. So rat's nest will be very useful to like update your polygons as you're changing the position of your wires, because wires can go through polygons, and then polygons will give space for the wires. And then rat's nest also updates all of the air wires. So for instance, if you have air wire, as I said before, it will give the minimum straight line distance between any, like the most close to same signals. So if you change the distances because you're arranging things around, you can do rat's nest, and then it will update their wires to the new closest. Yeah, because because if you did those things as you're like pretty much arranging things around all the time, it would take some time for the board to be constantly rendering new air wires and new polygon formats. Then apart from that, there's also this very useful command, which is repup at semicolon. If you only do repup and then the name of the thing that you want to delete, that will take the component or anything that you want from the board. But then I especially want to address repup at semicolon, because this will hide all the polygons from the board view. So at, if I'm not mistaken, stands for polygons, and semicolon stands for all, so you will take out all of the polygons, but don't be aware that will just hide the polygons, and you can repur them with rat's nest. So something that I commonly do while I'm doing a board is like use those two complementarily. So if I want to take a look at the polygon, I do rat's nest, but then you have polygons everywhere and they are kind of like polluting my view, I do repup at semicolon. And then another one, which is quite relevant, which is show at and then target name. So in this case, the at will highlight. So show at, you will highlight, not just you will show the component, but you will also highlight it. So you make a square around the component that you want to take a look at. So let's say, for example, that we have a signal called enable. If I do show at enable, it will do a giant square around every signal that is that has enable as its name. And then I can also use the wildcard character that you guys probably also saw on the week 2 to use on the name of the signal if I don't know what's the rest of the name of enable, and then I know that there's some sort of enable somewhere in the board, so I just do show at en, and then I put the wildcard symbol, and that will show me everything that has en in the beginning of the sentence. Okay, so that's it for the presentation, and now we're gonna go into the lab. But before that, I just want to go through a quick summary of the lab. So you pretty much start a new board layout from scratch, and then you set the dimensions of your board, you arrange the components around the board, and then you connect all those traces around between the components. You make sure your silk screen looks good, and then you check your design on DRC, which is the design rules checker, and make sure that it works. There's also more information on the document that I'll be posting on the chat if you don't have it already. And the lab is located on GitHub, just as every other lab. And here are the resources. So actually, I'll run through Ego a little bit just to give you the first steps on the lab. So yeah, I can send you the lab after I do this demonstration. So on the RoboJacket's electrical training repository on GitHub, you can simply download it. So you have, on the first steps of the lab, you have to download the zip of this, or you can also get it through Git or GitHub desktop, but I would just suggest just to download it. You downloaded it, and then after that, let me share my whole screen actually, because I think I can't go through the rest of my computer without exiting. Let me stop sharing quickly. Okay, you should be able now to see everything. So you download it, and then after you download it, you have the electrical trainer master. You will extract that file. You will enter on it, go to labs, week 4, and then on week 4, you will notice that it will have this firmware electrical training board, and that's an Ego file that you can open with Ego, and that's just a schematic. So what you actually need to do is create the board based on, create the PCB layout based on the schematic. And the way you can do that is you open the schematic, you have this, and then this is the button that you use for changing between schematic and board. By default, right now, we don't have the board. So as we print it, this will pop up and ask if we want to create PCB layout from the schematic. We click yes, and then here we go. You have the board that you can start working on. Also, for a little bit of context, the part of layers that I was talking about is right here on the top. So changing layers, the layer settings is everything about layers is pretty much in here. You also need to adjust the grid, because by default it will have mil instead of millimeters, and also sizes that you should also change, and those specific values are all in the lab. And then apart from that, here's the whole tab with all the tools that you need, and the only thing else that you also need to take into consideration is the manufacturing tab, which is here on the right. And as you can see, we didn't put any components, so the board is blank. Yeah, GRC is right here. And as you go through the lab, you can always make questions, and we'll be with our Ego on hands to try guiding you.